Okay, so this week we're going to be looking at databases, the front end and back end, as well as APIs. So this is going to kind of cover a whole suite of things surrounding web and web-based development. And so we'll jump right in and start out with SQL. So before we talk about SQL, we're going to talk about databases, and in this case, relational databases, and exactly what that means and what they are. So for the past 40 years, relational databases have formed the foundation of modern automated data processing. This class provides students with an overview of relational database concepts and principles. This is a really deep field, so be forewarned as you dive in that I'm going to cover the basics of this, but it goes, many engineers spend lifetimes as database engineers. Okay, some of the topics we're going to cover are the basic database systems architecture, DBMS software. We'll look at the relational model, so relational terms and concepts. And then, so that's going to be kind of the nuts and bolts of it. And then we'll look at designing a relational database. This will probably cover a little more in demo uh, and what normalization is. And then as well as database modeling, which gives us our EDR diagrams. Here are a few key terms that you'll need to know. So applications are the computer programs that users work with. Example, a payroll system or a registrar system. The database management system is very complex, powerful software that allows us to create databases, load data into databases, and retrieve data from databases. Examples of these would be MySQL, Oracle, Microsoft SQL Server. Structured query language is an internationally recognized standard database language that is used by all commercial databases. Okay, so let's say that you're a human resources worker at a small company and you use the browser on your PC to access a database. The signal that you send will first go to a web server, which then will hit an application server, which will then hit a database server and go and get the request from the database. Now, how is it that we actually communicate through all of this? It's through a lot of different protocols. So the first one that we hit is TCP/IP and HTTP, which we'll look at a little later this week. Then from the web server to the application server, sometimes the web server and the application server are actually wrapped into one server, but for this example, we're going to separate them. The API or the web server and application servers are accessed through an API, such as REST, SOAP, Java. And then SQL, from the application server to the database, we use SQL queries to pull the data, and MySQL database server will actually go out to the database, given those queries, and access the data. And then this will be returned all the way through. So this is the basic application architecture. We're going to drill down into it a little more later this week. So here is the use of relational databases versus basically Hadoop and NoSQL. So those are a little bit different databases. They're not relational. They're not formatted in the same way. But it turns out that actually, while this looks good for relational databases, looking at like 50 billion a year, open source is kind of making a dent in that. You can kind of see some of the relational databases having some upticks and downticks here. So the main reason that they are starting to see some issues is the cost. So here are some commercial products. MS Access is free. MySQL is free, but you can buy support. Microsoft SQL Server Enterprise Edition, the list price is about $15,000 per core. Oracle Enterprise Edition, list price is about $47,000 per core. So if I'm running a 4 CPU HP server and each CPU is a quad core, my server is using 16 cores, And so you can see the licensing gets pretty out there. So open source relational database management software, this was written by Monty Wadenius, and Monty formed the MySQL AG to govern it. This was purchased by Sun Microsystems, which was then purchased by Oracle. Monty branched out and created MariaDB, and now MySQL's big three are Oracle, MariaDB, and Percona. Okay, so let's take a look at the characteristics of a relational database. So the purpose of a database is to help people track things that interest them. Data is stored in tables, which have rows and columns like a normal Excel spreadsheet. A database stores both data and relationships. So this is the big key here for a database versus maybe like a normal Excel spreadsheet. Is that this isn't just going to be data stored in tables, but there will be relationships that bind these tables together. So a database may have multiple tables where each table stores data about a different thing. An example, we'd have a student table and a customer table. Each row in the table stores data about one occurrence of the thing of interest. Example, one student's data, one customer's data. A database stores metadata, or data about itself stored within itself. Example is the DBMS catalog. There is a table containing one row for every table in the database. And this is just internal to MySQL. They actually use tables to manage the tables that you create. So the relational model was introduced in 1970. This was created by E.F. Codd. He was an IBM systems engineer and mathematician. Codd's model is based on the branch of mathematics known as relational algebra. And this is now the standard model for most commercial relational database management software products. Okay, so there's a lot of terms surrounding the relational model. And we're going to go through all of them and what they mean. But we have entity, attribute, relation, composite key, primary key, surrogate key, and foreign key. And then we have the referential integrity constraint and normalization. So an entity is some identifiable person, place, thing, or event that users want to keep track of. That is, store data about. So we have customers, students, computers, cells. So an attribute is a fact or characteristic describing the occurrences of the entity. So we have the customer's first and last name, their middle initial. We'll have the student number, address, city zip, and so on. Okay, so now we'll look at the relationship or relations. So the relation DBMS products store data about entities in relations, which are a special type of table. A relation is a two-dimensional table that has the following characteristics. So rows contain data about an entity. Columns contain data about attributes of the entity. All entries in a column are of the same kind. Each column has a unique name. One cell of the table holds a single value. The order of the columns is unimportant. The order of the rows is unimportant. Those two are very important to the idea of relations. And no two rows may be identical. Every row has a column that uniquely identifies the row. And this is basically where a lot of the rules surrounding relations are built out of, and where we start to look at normalization and things like that. So this would be an example of a basic relation. Here, we've already broken some of the rules, is there's multiple phone numbers in employee number 400. So here, we have one entry per cell, but our biggest issue is that we have our table doesn't follow the entity model where an entity is described in each row. And so here you can see we've got the facts. So now row order matters, and that breaks the relational model. So here's a valid relation, but it just has values of a varying length. Okay, so now we're going to get into some of the terminology that is specific to the tables themselves. So a key is a combination of one or more columns that is used to identify rows in a relation. A composite key is a key that consists of two or more columns, also referred to as a concatenated key. A primary key is a candidate key selected as the primary means of identifying rows in a relation. There is only one primary key per relation. The primary key may be a composite. The ideal primary key is short, numeric, and never changes. So to give you an idea, in this table, our primary key would be the employee number. Partly for the short numeric, but also that it is unique to each entity that is entered in the relation. Whereas they may have the same phone number. If an old customer canceled their phone and signed up, you could basically get two people with the same number, or wind up with some. See, we have legal in the department that doubles for the last two entries. So the employee ID, or the primary key, is has to be unique. Okay, a surrogate key is an artificial column added to a relation to serve as the primary key. It's DBMS supplied, sequence number, short, numeric, and never changes, an ideal primary key. Has artificial values that are meaningless to the users. So in this case, for what we were looking at, this employee number is a legitimate primary key, and that it also is the number that the employee uses at work. But a surrogate key would be an artificial number that had nothing to do with the employee or didn't describe the employee in any way, but we use it as a key to distinguish each entity in the relation. Note the primary key of the relation is underlined below. So here's one without the surrogate key, this first point. So the rental property without a surrogate key, it's basically using the address as the primary key. And then in the next one, we have a rental property with a surrogate key, and there they just assigned a property ID. Okay, a foreign key is a primary key of one relation that is placed in another relation to form a link between the relations. A foreign key can be a single column or a composite key. The term refers to the fact that the key values are not primary to the relation in which they appear as foreign key values. A referential integrity constraint is a rule that limits the values of the foreign key to those already existing as primary key values in the corresponding relation. So in other words, the constraint keeps me from adding a row to a table if the value in a foreign key column is not on file. We'll go back and look at slide 21 here, but just to say it explicitly, I cannot insert a new product into a product table if it has an invalid value in the supplier ID column, referencing the supplier. So here on slide 21, without an employee ID, I cannot insert an employee. And that's basically what referential integrity constraint is stating. Okay, now we'll talk a little bit about designing a database. Again, I'll cover this a little more tomorrow. This is a really complex area, and so I'm going to give you the basics. We'll touch on it a little bit tomorrow, but this is something that employs whole fields of engineers. So data must be normalized, and we need to construct a data model, define all keys, and define all attributes. And the way we do this is through normalization. It's a structured, defined, detailed process. Prepares the database design to make sure it complies with COD's rules for the relational model. So the objective of normalization. is to arrange the data into a series of clearly defined, well-organized relations, each with a primary key. All attributes are fully dependent on the primary key, and each relation may have foreign keys referencing other relations. So, walking through it step by step, we have the first normal form, and that is to remove any multi-valued cells or any rows requiring a specific sequence. So this was in the Codd's first rules of relation, where he basically said things can't be dependent on row sequencing, and we can't have more than one thing in the cell. The second normal form is for entities with composite keys, make sure that all attributes are dependent on the full key. And then third normal form, make sure that no attributes are dependent on any other non-key attributes. Okay, now we're going to take a look at data modeling. And here are some of the symbols that you'll use with data modeling. We have the entity with an entity name, the primary key, and the attributes. So the entity name sitting on top of the box, and then we have the primary key, and then attributes in the lighter shaded area. And then we also have cardinality and optionality symbols. We'll talk about those now. So cardinality is how many of these are related to how many of those, or these. Typically 0, 1, or many is how we describe it, and on both ends of the relationship. Optionality is the relationship mandatory or optional? And so this can be one or more, or for an optional relationship, you could have 0. Okay, here we have an example of an ERD diagram. And you can see all the relations that we have. We can identify their primary keys. And here we have a composite primary key. We can identify their attributes. And then we have the symbols that describe cardinality, as well as the optionality or mandatory. So here you can see option, that's represented by the circle. This is 1 to many, and it's red left to right, or many to 1 in this case if we went right to left. Here is what a mandatory symbol looks like. Again, optional, so this is 1 to many. There must be 1 of these at all times, but there could be 0 of these. But this one can map only one entity in the customer relation to one entity in the customer artist. Here we have a mandatory 1 to many, so there must be at least one entity in each of these tables. So we can check the null status, and this indicates whether or not the value of the column can be null. Here are some generic data types that can be represented by the attributes, as well as the primary keys. So in summary, databases are ubiquitous, meaning they're found everywhere. DBMS software is extremely powerful and complex. Oracle and MS SQL servers are expensive yet widely used. MySQL is free and is also widely used. Relational database software holds 90% of the market share, but NoSQL and Hadoop are booming, so folks can handle big data. Database design requires specialized skills. You can see down here on the bottom we have careers in databases. Database administration is more of the administration side, but then and then also application developer, That would be more on the querying side, which we'll get into with SQL. But you can see we have data architect and data scientist. These are really where it gets pretty deep, especially the data architect, who is responsible for designing those databases. And then data scientist uses databases for analytics.